All right, so welcome everyone to the second session of the day, which will be a focus on transaction fee mechanisms. And our first speaker will be Matt Weinberg from Princeton.
All right. Is working? Not working. Working. OK, cool. All right, so first, thanks for having me. So this talk is going to be on revisiting the primitives of transaction fee mechanism design. It's joint work with Adityan Ganesh, who is here, and Clay Thomas, who's at Microsoft Research and not here. So what I'm going to do in this talk, so first, in comparison to the morning, there is going to be like a lot more text on the slides. There's no proofs or anything, but it is going to be maybe a little bit more technical. I'm going to give a brief recap of transaction fee mechanism design first, just because I'm not positive what everyone's background is. Then I will overview the primitives of transaction fee mechanism design as of until very recently. And in particular, I think two things I would take away from that is that I think EIP 1559, I think, was rightly considered the gold standard by those definitions. And the cryptographic second price auction, basically like a second price auction with cryptography, was not. And then I'm going to argue that maybe we should revisit those and consider things a little bit differently. One thing this will do is highlight a novel issue with EIP 1559. And a second thing it'll do is, I think, fix maybe like a silly mistake in the definitions that will show that the cryptographic second price auction is actually not that bad. And there is a theorem. I'll state the theorem, which, like everything else in this line of works, is saying nothing is perfect. But I will try and argue that maybe the cryptographic second price auction is pretty good. OK, so let me just give a brief overview of transaction fee mechanism design. So I think this is motivated by the following question, which is just how do we decide what transactions get included in a block? In general, just block space is a scarce resource. So we need some way to decide what will get included in blocks. There is a cost. Because the more information you include, the longer it takes to propagate. That matters. And until fairly recently, like one way to look at what everyone was doing is, I would say, it's just a first price auction. So when you put that, what was going on in auction theory language as a transaction fee, call that a bid instead of a transaction fee. The block creator will include the highest bids because they want to get as much money as possible. And maybe there's a block size limit. I'm not going to worry too much about that for this talk. Maybe they include a small reserve because it actually costs them something to transmit more bits. I'm not going to focus too much on that. And then the transactions just pay this fee to the block creator. So it's a pay your bid. It's really, in auction theory language, a first price auction. And what's wrong with this? So there's this blog post from a while ago by Vitalik that I read, that I would recommend reading if you're curious to get like a good intro from the Ethereum perspective side of like why care about this. So I won't maybe flip through, but there's like a couple big picture justifications that Vitalik had when he started this slide or this post. And I would maybe summarize two of the main things I took away from reading those is, one, you really want to incentivize miners to follow the protocol. That was a first order concern from the stuff listed there. And two, it seemed like the users really wanted straightforward bidding. So they wanted to know how much, what is the actual cost of including my transaction? I would like to pay that cost. I would not like to have to figure out what's the right thing to bid. OK, and so the lens I'm going to use for this talk is I'm actually going to merge these into a single goal. And so so I'm not trying to claim this is like everyone's lens, but I'm saying this is the lens I want to use, is that the most important thing to me for this talk is I would love to be able to just tell the users, it's OK, just bid your value. In particular, don't worry about strategizing what to bid. It doesn't help. Don't worry about the miner cheating because it doesn't benefit them to hurt you. And you don't need to go out and try to make buddies with miners because you're not able to jointly profit by doing that in the first place. Okay, and so I would say, like if these things hold, it seems sensible to just say, yeah, just bid your value. Don't think hard about how to bid. Don't worry about the auction the miner said they're going to do is not actually the auction they're going to do. And don't worry about doing stuff outside the game. And so I'll give you maybe just like a very quick intro for people who haven't thought about this before. The natural thing that someone would try if they know a little bit of auction theory and they heard that the first price auction was not a good idea is they say, maybe we should use the second price auction. And what's nice about that is that if you're familiar with some auction theory is that it is incentive compatible, so it's easy as a user to bid. And what's wrong with that is that the block creator does not actually want to implement the auction. So through this lens I'm proposing, it would say like, doesn't really matter that it's incentive compatible to bid your value because the miner's not going to run a second price auction anyway. And so here's a quick example that just says, you know, sort of like, yeah, the miner should insert some fake bids. If they insert some fake bids, they're going to get some more revenue. Okay, and so I would say the problem here is that you can't just say, yeah, it's a truthful auction, bid my value, because the miner's not going to run a second price auction. And so it's actually, you have to worry about what to bid. A second thing you might think of is maybe I should run a posted price mechanism. So somehow this is similar to EIP 1559, except with no burn, where you'd say the protocol sets some price, the miner picks some transactions to include, they each pay some price. And again, what's good about that is that it's easy for users. If your value is bigger than P, you should bid. If not, you should not bid. The block creator can't insert fake bids to help them in any way. They're getting P per transaction no matter what they do. Censoring doesn't help them because that's just going to get them less money. And what's wrong with this is what a block creator can do is get together with a bidder off-chain. And the bidder can be like, hey, I'm actually not willing to pay P, but I'd be willing to pay P over 2. And then they'd get together and say, yeah, fine. Why don't you go ahead, bid in the auction. I'll give you a refund of, you know, like 3P over 4 off-chain. And then everyone's happy, and so they jointly profit. And so, again, through this lens, what this means is that you should go out and make buddies with miners, because then you can get better prices and everyone can jointly profit. Okay, and so then there's EIP 1559. So there's 2 levels to it. I'll try and focus on the more interesting part. So the more interesting part is what's on the screen, which is that there's a fixed price P, just like before, and the miner still picks any set of, in most K, transactions to include. Now every transaction gets burned. So the miner makes no money no matter what. And what this gets right is all of the 3 things that I mentioned so far. So it's easy as a user to bid. If your value exceeds P, you should do it. The miner is getting no revenue no matter what they do, so they don't have any incentive to censor. They don't have any incentive to insert fake bids. And there is no way to collude off-chain with the miner to do better, because someone's got to burn P in order for your transaction to be included. And if your value is less than P, then there's no way for you and the miner to get together and somehow burn less than P. Okay, so there's this is maybe just like a quick note that's sort of like, yeah, EIP 1559 is more complicated because, yeah, it could be that the demand exceeds the supply, and it gracefully handles that, but that's not the focus for this talk. So I would summarize the state of affairs as just being that by these measures, EIP 1559 with unlimited supply, or in the ideal case, is good. So you can really tell a user in that case, just bid your value, really. Don't worry about how to optimize your bid. Don't worry about the miner cheating you. And it actually doesn't help you to go make buddies with miners either. OK, so that's maybe an overview. So now getting into the primitive. So what's the formal model that we use to think about this? So you should think of a transaction fee mechanism as taking a input from bidders. So it takes from each bidder, what is your bid? What the miner can do is they can cheat. So a miner can censor bids. Okay, so they have the power to do that. They can pretend they didn't hear about it. They can also insert their own bids. So they can pretend to be a bidder. Nobody would know that actually this bid came from a miner. But these are the only 2 ways they can change it. They can't just decide, hey, you said you bid 5. I've decided your bid is 10. but they can definitely do these two things. And after this, there's some allocation rule A. A is going to say based on the bids, here's what gets included. There's some payment rule P that says based on the bids, this is how much everyone pays. And then there's some revenue R that gets to the miner. So because you can burn things, it may not be the case that the sum of the prices is equal to R, but R will be something less than that. And there were 3/4 criteria proposed in the works that got this started, which is that the auction should be dominant strategy incentive compatible. So users should not want to strategize when they think about what bids to submit. And then there's this phrase they call myopic miner incentive compatible, which says that when the miner sees the bids B and then decides, do I want to censor? Do I not want to censor? Do I want to insert a fake bid, not insert a fake bid? They should never want to insert a fake bid. They should never want to censor. And then these collusion resistance notions, they're meaningfully distinct, but I would say generally what they say is that certain collusions that include the miner should not be able to profit. So informally, I'm using this to capture, it doesn't actually help you to go make buddies with a miner, because even if you were to do that, you wouldn't be able to jointly profit. Okay, so again, so let me focus on, so there's EIP 1559 with unlimited supply, so I'm ignoring the possibility that the base fee is too low and therefore there's competition. And it satisfies all of these properties. Okay, so I would say that if you stick with the primitives we have, that would say you can't do better than EIP 1559 in the unlimited supply setting. And kind of like the only drawback is that you have to figure out what to do when supply is limited. And okay, so the cryptographic second price auction, so what do I mean by this? I just mean that when the miner is deciding whether to insert fake bids or whether to censor, the real bids are still encrypted, so they can't use that information. And so there was this paper by Shicheng and Wu that showed that actually, even though intuitively this seems like what can the miner do, everything's encrypted, they said, well, it's technically not MMIC, because even if the miner doesn't know the bids, they might want to set a reserve. And technically, a second price auction without a hard-coded reserve, or with a reserve that's not correct, they may want to set their own reserve. So there is something that the miner might want to do, even if they don't know the bids. And then there's these series of papers that show that when you have limited supply, there is no way to satisfy all three properties. And yeah, so that's the state of affairs. So now I'm just going to hint at what's new about this talk. So what's the new perspective I want to share? So first, I do want to give a new way to look at a new concern and argue that EIP 1559, I think even in the unlimited supply setting, I don't think should be like a gold perfect standard. I also want to argue that if we, cryptographic second price auction not being MMIC to me feels more like a technicality. I think we should maybe fix the definition, and that maybe the cryptographic second price auction actually is pretty good. And the third thing I want to do is just revisit the current notions of collusion resistance. I don't know that I want to say, I think they're too strong. I don't know that I believe that. But I do want to give a little bit of a different perspective to argue that maybe something weaker is still meaningful. Okay, so let me go through what do I think is missing from the previous analysis of EIP 1559. And the question I want to ask is, and so like if this were a lecture, I would actually pause for a few minutes and ask you to seriously think about this. But say that you are a miner in EIP 1559. I want to really ask, what would you do? So that the answer is not, oh, well, MEV messes everything up. I want to take the model literally. There's just a bunch of bids. It's simple transactions. And what would you do? So one thing you might tell me is like, well, I can follow the protocol and get zero revenue. So I'd say, OK, that's one option. Another thing you could do, you could say like, oh, I'm going to be clever. I'm going to include fake bids. I'm going to censor bids. But we know that still gets you zero revenue because EIP 1559 is MMIC. And what I want to argue you should do is you should just like state off chain, everyone's got to pay me $10 if you want to be included. And that's a credible threat because, you know, like what's going to happen if I, if I stick to this, the worst thing that's going to happen is I get 0, right? But I was going to get 0 anyway. So if I do this, this will get me a chance of some revenue. And I would say this is the kind of thing that I think should be considered. And then when I get to the last bit of the talk, I'll give an actual model to think about this. OK, so through, I would say, the informal lens, I would say, so EIP 1559 still has these 3 ways of saying, don't strategize, don't worry, just bid your value. But I would say maybe what we're pointing out is that, yeah, you have to worry about a miner trying to do their own thing off-chain. So they're not colluding with you off-chain. That will never help. But the miners doing their own thing off-chain to kind of like hijack their own auction in EIP 1559. And I think that's a real thing that you should be concerned about. And so I can't tell you just bid your value, ignore whatever's going on. You may need to look off-chain to find what's really going on. OK, so what about the cryptographic second price auction? So I mentioned that technically it's not MMIC because the miner may want to insert a reserve even though they don't know the bids. And here the solution is really more of a, like, let's just go back and change the model a bit. But the clear solution in this case is, like, let's just let the miner set a reserve. That doesn't hurt the bidders if the reserve is set without knowledge of the bidder's bids. And so here's the proposal. So I copy-pasted the model I initially posed, and I just bolded, like, some change, which is like, let's just ask the miner for input. And instead of calling it fake bids, we'll say, yeah, there is a space for the miner to provide input. They do set this input after seeing what the bidders provide. But like if the bids are encrypted, then they don't get any information when they do this. And basically just saying, like, yeah, like, I think this should be the model. And if this is the model, then I'll give you a definition where you can say, like, yeah, the second price auction, even though you're letting the miner set a reserve after seeing encrypted bids, that can still be MMIC. OK, and in particular, if I really stick to this just bid your value lens, I would say, like, I think the cryptographic second price auction is actually pretty good in the sense that I really would tell someone, like, look, your bid's going to be encrypted. So first, it's a second price auction, so don't need to strategize. Second, your bid's going to be encrypted. And the miner can't do anything when all they see is your encrypted bid. So you don't have to worry about the miner cheating to hurt you because they saw your bid. And second price auction with reserve, like, is already the revenue optimal mechanism in a lot of cases. So you don't have to worry about the miner trying to hijack their own revenue optimal auction by doing something off chain. And the don't go out and try and make buddies with miners, it's like, it's like a little bit tricky in the sense that second price auctions are OCA proof, so they do satisfy one of the, one of the collusion resistance notions from previous. They're not this CSEP, so they're not fully collusion resistant. And I'll mention what we're proposing is kind of like an intermediate notion of like Bayesian collusion resistant, and the second price auction is Bayesian collusion resistant. So basically here, what I was trying to get at is that I do think the cryptographic second price auction is pretty good. I understand that it may not be technically feasible, and that there's a lot of challenges in implementing it, but at least from the TFM perspective, previously the definition said it was actually not good. I'm trying to argue I think it is actually good, at least by those definitions. Or sorry, at least by the TFM perspective. OK, and then the last new perspective I want to share is on collusion resistance. So let's revisit the posted price mechanism. So we said that what's happening here is, again, there's a posted price of P, and it's set by the protocol, and everyone who's included pays P. The miner gets all of that. And we said the problem was that they might be able to collude, and the bidders would bid P on chain, and the miner would pay them back 3P over 4. So here's a question I would want to ask, is I would say, well, how did the miner and the bidders agree on a refund of 3p over 4. So like what would have happened if the bidders just said, hey, actually my value is p over 8, it's not p over 2. Then a refund of 3p over 4 wouldn't have gotten them to bid on chain. Would the miner have offered them a refund of 9p over 10? Or like what would have happened there? And so this is where I'm not providing, I'm not saying I have a clear answer to this, but I'd say one answer is you might say, look, if like, the miner is Coinbase and the bidders are Coinbase, then they know each other's values. They are literally the same entity. And so this, this thought experiment of like, well, what if the bidders pretended to have a value less than what they said is just not a meaningful thought experiment to go through. So I think if that's what you're really concerned about, is you're concerned about people really going out and merging into being the same entity and not having private information from each other, then you do want the original definitions. You don't want the new thing I'm proposing. But I would say, like, if what you're concerned about is like, no, look, the miner is a separate entity. The bidders are a separate entity. The bidders have private information the same way we always think of bidders of having private information. And maybe the collusion I'm worried about is, oh, they're going to collude. There's going to be some Bayes-Nash equilibrium where the miner has a collusion protocol in mind based on what the bidders tell them their value is, and then they're going to collude together, and they might hurt the other bidders, but they're still going to be interacting in Bayes-Nash equilibrium themselves. Then maybe you should just rethink what it means to have a profitable collusion. And so I would argue that depending on exactly what your threat model is, maybe you really do want the original definitions if you're concerned about this very strong notion of collusion. Or maybe if you're not concerned about quite that, but you're concerned about separate entities getting together and colluding but still not really trusting each other, maybe you would be OK with something a little weaker. OK. So now I will get into, that was kind of like more the intuitive takeaways of what I want. Now I'm just going to tell you a formal model, and this will wrap up the talk. So, OK, so what's the only difference from what I proposed before? So I said first, before our work, everything that was not in bold was the model. Then I proposed, in order to let the miner set a reserve without that violating MMIC, we should just let the miner provide input. So we said, fine. The only new thing I'm going to do so that I can actually make a definition of what does it mean for a miner to not want to hijack their own auction, and what would it mean for a miner and bidders who don't share private information to collude, I'm just going to do what we typically do in Bayesian mechanism design, is just say the miner has a Bayesian prior over what the bids are going to look like. Okay, and so this is the standard model that you would use to do auction theory outside of the blockchain space whenever you're thinking about optimizing revenue. And so that's the only thing I'm adding. So I'm adding only the things in bold. One is we should just say, yeah, the miner should be able to provide some input. Two is when the miner is optimizing, we should let them have a prior because that's what we typically do in auction design. OK, and so now we can revisit, like, what are the definitions we want? So one of them is still the same user incentive compatible. So this is more like a syntax change than a substantive change, which just says that, like, yeah, it should be the case that I can recommend an input for the miner results in user simplicity if, when the miner uses that input, it's a dominant strategy for the bidders to bid their true values. It's basically the same as the original definition, but we have to change the syntax. OK, so now I can talk about what would it mean for miner input M and a Bayes-Nash B. So the bidders are going to play according to some strategy profile once the miner sets the input M. And so this is my stab at recovering MMIC in the new model, is just saying once B is fixed, now I can ask, what does the miner want to do? And so I would say, like, well, the miner could change their input. They could not use M. They could do M prime instead. They can also insert fake bids and censor bids. And on-chain simple is capturing exactly these on-chain deviations. So it's saying, once I've told you that the bidders are going to play in Bayes-Nash B, do you want to cheat and use a different input? Do you want to cheat and censor bids? Do you want to cheat and insert fake bids? And the answer should be no, and then it's on-chain simple. This is basically the same as MMIC with more syntax. It's more permissive just because it lets the miner input something. Okay, and then here is the actual new definition. So the new definition that captures what I'm saying is the issue with EIP 1559, I will call off-chain influence proof. Okay, so this is not like off-chain collusion. This is just a miner who is trying to maximize their expected revenue. And what they could do is they could say, okay, rather than use input M and have bidders play in Bayes Nash B, I could instead use input M prime, that's a different input, induce a different Bayes Nash B prime, and I could run my entire thing off chain. Why do I have to run it on chain? And so what this is saying is that your equilibrium M and B is off-chain influence proof in the sense that I would expect a miner to not hijack their own auction with something different using off-chain payments if this is the best revenue they can possibly get among anything that even those that use off-chain payments. Okay, so for example, a second price auction with reserve that is optimally set, that is the revenue optimal auction among all auctions and all Bayes Nash equilibria for in certain settings. And so if that is the on-chain auction, there is nothing the miner can do off-chain to get more revenue. Because whatever they do off-chain, even with off-chain payments, they're inducing some Bayes Nash equilibrium of some auction. And they're not going to do better than the optimal one. Okay, and then maybe last technical law thing is just say this. I didn't give a formal definition of what does it mean to be Bayesian collusion resistant. But it happens to be implied by this off-chain influence proof. So let me skip this part of the formality since I think I have a minute left to wrap up. So basically what I want to say is that, like, yeah, it would be good to just say I have a TFM, and it should be the case that no matter what prior the miner has, there is something they can do that induces truthful bidding for users. They don't want to cheat on chain. They don't want to hijack themselves off chain. Not wanting to hijack themselves off chain implies this Bayesian collusion resistance. That would be great. And so the cryptographic second price auction has that property. I would also note this is even with limited supply. So what that means is reducing from the really strong collusion resistance to this Bayesian collusion resistance does let you do something with limited supply, whereas you couldn't do that even with cryptography with the strong collusion resistance. But even with unlimited supply, there is no way to satisfy the strong collusion resistance properties and the new one I proposed. So that is distinct from the previous case where EIP 1559 is satisfying everything you want with unlimited supply. Okay, and then just to remind you, right, from all of this is that I really think that if you satisfy all of these properties, I think that it is now more safe to go and tell a bidder, just bid your value, it's really okay. Don't strategize for the auction because it's truthful. Don't worry about miners cheating you on chain because it doesn't help them. Don't worry about, don't go out and collude with miners because it won't help you or them. And don't worry about off-chain mechanisms because the miner's already doing the optimal thing on-chain. Okay, so this is the pitch to try and get there. And so maybe let me, since I think I just ran out of time, let me leave this up and maybe I'll just note for future work, I'm the kind of person who does think, I think it's really important to study the core setting to death, even though I understand that MEV has kind of ruined all of this in the first place. It is separately also important to understand, like, what does MEV mean for transaction fee mechanism design. It's good that, people are doing that. But I think it's good to just be thinking really, really hard about what TFMs should be doing from both of those perspectives. And this one is very much along the lines of the first one. So that's it.
Oh, I have a quick one.
Oh, sorry.
Hey. Yeah, so just to make sure I kind of understand the flow here, once the miner's trying to set the value M, do they observe the bids and then set M, or do they set them based on the prior that they have for the bidder's values?
Good question. So they would set M based on the bids. So what I would think of it as, if your mechanism is a plain text mechanism, then you would see the bids in plain text, and then you would set M. So a second price auction run like this would not be MMIC, because you would set the reserve after you saw the bids to be just below the highest. If the bids are encrypted, you should think of it as you see the encrypted bids, and then you set this M. And so at that point, all you really know is the prior and a bunch of encrypted bids, and so you would set M based on that.
So just seeing them, like, it wouldn't matter how many bids you see or whatever, like, would that come into factor when you're
So
calculating them?
great question. So it turns out that for optimal auction design, if you believe they're from the same prior, it would not impact the optimal reserve you choose to set. If, depending on exactly what your prior is, if it's not a product distribution or it's not whatever, then it could. I would interpret our choice to do that as just saying, like, it's like the minimum edit distance fix to the weird interaction between saying somehow a cryptographic second price auction is not MMIC. To just say sort of like this idea of the miner sets a fake bid after seeing stuff, and somehow that's a problem, even if they don't know what it means. We say, like, just call one of the fake bids a reserve or whatever. So I would interpret it more like it's trying to capture a fake bid that's okay, without being obviously problematic. Yeah.
Thanks.
And our second speaker for the session is Abdu Enjoy from NYU.
Thank you very much. I echo Matt's point to look at the core setting. And what I'm going to do is even ask questions of why. So the title is a bit of an oversell, Transaction Execution Mechanisms. But so how do I push this forward? Green. Yeah, so really the transaction fee mechanism that we have really asks the question of how do we include and what transactions should we include, how do we set transaction fees to include, to decide which transaction will be included or not when we have congestion. The solution that has been found around this is to find ways to do parallelization. So sharding is one example. There are other things as well, but often when parallelization comes as well, you can still face the issue of some state of the blockchain being contested. Now, there are words circulating around like local fee markets. What are local fee markets? We try to address that and how we should think about it. When should we even consider something like local fee markets in the first place? An example, so this is on one famous local fee market. Now, I haven't seen any like technical documentation to say how it's actually implemented, but this comes from the Umbra research points, where clients send transactions. There is a server that sends transaction packets to different validators, and they send it to different slots. Now, there is different execution threads that come together. So let's say execution thread 1 and 2, and they have these transactions. These transactions touch some object, some contract, and give them names, A, B, and C. So you can have a transaction that can have multiple contracts that is touching, for example, combined, A, B, and C, D only one, C, J. Now, when they execute, what is going to happen in parallel in thread 1 and thread 2, they look at these transactions, starting with the very first one, A, B, and C, so locks every other transactions that are touching C, so that is those ones with the locks, and then looks at those that don't have any contention and executes them. That's the post-execution phase, and the next iteration considers after this. So this comes just pure mechanic of just doing this, and now there is no other kind of economic mechanism to think first, how do I even allocate transactions to one thread, and second, how should I price these to be executed? Another example that comes as well, where this is needed, is in these architectures where they try also to have something like directed acyclic graph-based protocols. So in these blockchains, what they do is, instead of just having one chain of blocks that come together, they divide it in different, in a DAG where they are linked through some causal history. And then afterwards, from these different parties that have different mini blocks, they need to choose an order to how they will execute at the end of the day the transactions. So there is some consensus needed for inclusion, but the execution afterwards happens. It needs to follow a deterministic rule and some causal history, but beyond that, there is a lot of choice to make between how transaction to execute these. And okay, so it's not coming. Oh, all right. And lastly, I think also once sharding is implemented as well, there is still the need to have consensus for whole transactions, and there is also a decision of, do we want to have just one global ordering, one global fee mechanism for each, or should we have more localized fee mechanism? And if also when you consider some things like multiple proposals, et cetera, you have always this issue of how do we combine different transactions together. Now, this is different. I want to just mention from people who talked about execution tickets and so forth. It's more of the following idea that we're going to think of. So think you have, you can find a way to have many separate lanes, okay? And these lanes are also defined by the protocol. This is execution in parallel. But the main challenge also in the blockchain setting is that there is the consensus constraint, is that you need consensus, so that's where you decide inclusion. So inclusion is the first part that I think a transaction fee mechanism that we have now solve, but we have also the issue of execution, which at the end of the day matters for users. So the first question we address is, when should parallel transaction services be priced differently? Okay, so I'm going to be focusing mostly on the macroeconomic aspects of this question rather than the incentive compatibility issues. These incentive compatibility issues will come up as equilibrium conditions in the system with when people submit their transactions. And the second is, can we consider something, since we know how to do EIP 59, which to me is pretty much like a posted price mechanism, essentially. It's like the tip, in good times, the tip is close to zero. In good times, when it's able to price inclusion well, how can we, what is an optimal, approximate optimal mechanism to price parallel execution different? All right, so let me give an example here. So imagine this is an example where you have, we are able to define two queues, right? So you can think of it, there are many different applications. So imagine these are all things that can be, these queues, they are, let's say, imagine one of them, the 10, the high value one, is for an NFT contract. They are all trying to buy, and the 6, the cheaper one, is for like regular, let's say, native token transactions. But for this simple example, we know that the expected value are different. We know the first one is 10, and the second one is 6, and we have here these groups of transactions, okay? Now, imagine we have the following constraint, is that we can execute in parallel. However, the blockchain, for inclusion, we can take 5 transactions at a time. That's the limited capacity because block space is limited. Okay, that's the first part that is a constraint. Then what happens, because the QA has highest expected value, but when we start look for inclusion, there will be more transactions from A included. Okay, if we just do one global ordering, just like something like EIP 59 or even any types of like just a global auction will do that. But B could be processed in parallel, but because of the inclusion constraint, will not go in. And this can get longer and longer. Okay, so this is an example. So A4 and A5 are two others that just came after, but because they're paying more, if you just do one global order, is gonna be, these are the 5 that will fit in, and it gets longer, even if B. Now, this is inefficient from a perspective when there are delay costs. It's inefficient because it doesn't solve the socially optimal thing because you are missing out on the B transaction who you could be processed immediately. All right, so in this simple situation where we know the valuations, right, a solution is easy, right? If you knew the valuations, one thing you could do, and you care about delays is to say, okay, let me scale each of these transactions by the valuation, right? I know the expectations, so let me divide by that. So I'm gonna consider these transactions as if they are paying a different price. So I take the top ones, I divide each of them by 10, and the B ones, I divide each of them by 6. Now I'm gonna have these like virtual, it's like they've paid virtual bids that they do, okay? And then I can execute based on this order, right? So when I execute based on this order now, you see that they are becoming more balanced. And of course, this is not a realistic example because we don't know their expected values. Can we have a good market signal for it? So when we do this, what I call market value weighted ordering, then you start seeing that there is more balance, that in our inclusion phase, where we need to go to consensus, that we need to decide which transaction to include, you will have more transactions from B as well coming and a more balanced execution order from this same example. Now, the challenge is, right, how can we generalize this idea? So, right, since the market values are unknown, are there a good signal for it, okay? I argue that yes, often, like in 2022, Ethereum blockchain was clogged. We have 2,000 gas because of the Bored Ape Yacht Club launch for 10 minutes, okay? For 2 hours, okay? And no native transaction passed during that time, okay? So we can have a good sense of how people are valuing that. What if there are several queues? What if these queues, how do you define these queues endogenously as well? And how do you define those, right? And especially sometimes it's obvious because the protocol itself decides to which thread they want to send it, but can they be defined more broadly? All right, so to answer this, I'm gonna consider a model to think of these, and I'm gonna argue that the global ordering will just serve the queue that will be the highest paying, that will be the most congested, but it's inefficient, okay? While relative pricing can be efficient. So here I'm gonna be focusing on posted prices. There won't be these incentive issues, but there will be equilibrium conditions that capture incentives of users. So I'm gonna consider a capacity-constrained blockchain execution system where I'm gonna model it as NQ system where customers are sensitive to delay, some just like mathematical assumptions. We have IID execution times, user submit transactions to one queue, but they will be all considered for consensus. Okay, there is an arrival rate or market size, sigma I, so you can think how many people are coming into this market. If it's larger, it's more need, like say this is like a native transaction token, but if it's smaller, it's a less market size. And then we're gonna assume here the choice of, let's say we fix uniform prices for each submarket or QI. Okay, so thinking of a base fee, in this situation where there is no issues around incentives, valuations, distribution is no, and there is no private information is fine for our purpose. Okay, so other just notations and definition language. So users differ in their evaluations, but this essentially gives us a distribution essentially and how much the arrival rate will affects efficiency of the system. So we're gonna have valuation that are IID and they are drawn from different distributions. So you can think of these valuations for different of these queues are different distribution. There might be some that are very valued, some less so, where people will be willing to pay more, others will be willing to pay less. So from this distribution now, we're gonna have the arrival rate lambda that depends on the distribution of valuations, and we can define the marginal value of the user who is marginally paying, right? So the marginal value, this is the user who will be at the marginally accepted given at the arrival rate lambda I. This will be this marginal valuation V for execution of their transaction. Okay, some more, the delays matter, so people value their execution of their transactions, they differ in that, but they can have two costs that you can think of. Some are expected delay discount functions, delay discounts, so the more you wait the less valuable it is. So think of this as something that is not very sensitive type of cost. It's like, oh, I'm sending a transaction to my friend. Yeah, I'm happy to delay, but fine. But you can have these linear delay costs, or that can even have fixed costs associated to them, which is, oh, what if I lose an MEV opportunity because I'm delayed? And they pay their price. All right, so now let's talk about the blockchain system constraint. One of them, which is what I call the local demand equilibrium, which is coming from parallel execution, is that in any Nash equilibrium in the system, users will join if and only if demand in the market satisfies the following, is that their utility is going to be equal to their outside option here, which for this example is 0, and which is actually which is what would be an incentive-compatible mechanism do. So you can have two interpretations of this. One is, if users are allowed in some applications to choose where they are sending it, so let's say think of in the multi-proposer case, or sharding where they are choosing where they are submitting what type of transaction they want to send, then you can think of this as an equilibrium condition coming from the users entering and exiting across queues to look at which the ones that are mispriced or not, up until this value equals the outside option. Another interpretation is, if for those more, I would say, centralized applications where the protocol itself dictates to which scheduler things are going, you can think of this as a within an equilibrium within this queue itself. It means that if this one is mispriced, the people are having higher value, that means still you will have more people coming in. Let's say if there is an arbitrary opportunity, you'll have more people coming in to try to take advantage of that. And the other constraint of this is what I call the global inclusion constraint, is that now these different arrival rates in these different queues, there is a maximum total amount of transaction, or here in the specific application that we have, it's computational resources that are up to a limit, okay? So there is a maximum total amount of people that can be served, because we need consensus in the first place, so and the capacity is limited. And we're gonna talk about what happens when the capacity is limited. So you can think kappa here, the good example would be, let's say, the 30 million gas, okay? All right, so let's look at a case of what would be revenue maximization. Revenue maximization would be, we're gonna look at the protocol maximizing its revenue by adding up the sum of fees that they are collecting from each of these queues. The sum of these fees collected would be the bids would be the bids, but here it would be lambda I, the arrival rates, times the prices that are paid, and added over all the queues that they decide to serve as well, because they can choose not to serve a certain queue. Okay, S is the set of queues that they will serve, and the prices by equilibrium, by the local equilibrium condition, are the following. Now, so in the paper, I should prove this proposition, is that if there is a lot of global congestion, so the way you think about it, there is a threshold capacity kappa, low, below which the revenue maximizing relative prices would allocate capacity to the highest price queue. So that you will only serve to the highest price queue in this situation. So think of this is the case of even if whether it is relative price or a uniform price, you will serve the highest price queue. So you can think of these are the example of the May 2022 example that I gave where no other transaction is coming in. This is like the example of the global order as well. Okay? However, efficient allocations work differently. An efficient allocation that would be achieved would serve all queues. So that's what I show as well. Efficiency is different because efficiency, instead of maximizing all fees, we look at the delay costs that are processing all the transactions coming from the board or the one queue only will put on the whole network. So under certain very general conditions, then the relative price social optimum, the efficient one, will allocate capacity to all queues by lowering prices for certain and increasing for others. Now, what is the intuition What would be determining this relative price in this posted price example? I argue that in this posted price simple example can give us insights into how we can design mechanisms that are more expressive, that will be heterogeneous. The prices will capture three things. There is relative prices. One will be a local delay externality. So this would be the externality that the processing a transaction puts locally on all the others that will be just proportional to the value that people are putting on this transaction. Another is the additive delay cost. This would be large if, let's say, this was like a MEV type of opportunity. And finally, there is an externality that is coming out from the globally, what externality you are facing by including this transaction for consensus rather than others. And this can be large, for example, when the network is congested. Now, related to the examples that I showed above earlier is you can play with certain examples by specifying the model further. Those were the general results, but you can specify the model further to pick certain examples of, let's say, valuations and distributions that leads to these valuations. For example, if we consider distributions where we have execution times that follow an exponential distribution, then we can find the following relative prices. These following relative prices between the different queues, the interesting thing is that when you have local congestion dominating global congestion, meaning that this global shadow price is negligible relative price, then you can find that the relative prices of different queues are proportional to the arrival rates and the market size. And the idea is that if we can have a valuation, a market signal of these ratios, lambda I over lambda j times the market sizes ratios inversely, then we can find relative pricing mechanisms that work. Now, in practice, one way to think of this, the lambda I over alpha I is essentially what historically, if this is something that is persistent, people have paid in total gas units for a certain contract or an object. So in summary, okay, how could these ideas lead to maybe implementation of things such as local free markets? One thing to do is we can define a notion of what a local value is. Now for that, I think these queues need to be defined. There are different architectures, so they depend all on the application. They can be a state or a contract or object for object-centric ones. And this will be the best proxy for them. It will be the total gas paid in previous blocks, reading or writing it. I know whenever we say historical data, often in the blockchain space, the question is, oh, but can't this be manipulated? Well, EIP 1559 uses historical data as well. And I think if the network, there is some persistence happening sometimes when people are trying to buy Supreme shoes all at the same time. So there is some persistence coming. So there are some implementation things to decide, but one form of how you could apply something like this is to define and update with an EIP 1559 type mechanism a reference base fee, which would be the inclusion fee essentially. Okay? And then each transaction will be assigned to a queue of the contract with highest local value it reads or writes. So for example, imagine a transaction is touching many different, referencing many different contracts. You can define the one that is the hottest contract, essentially, that it is touching as the queue where it essentially needs to go when we consider it for execution and for pricing. And we can define base fees then, given these queues, they don't need to be many queues, you can define them by percentiles. These are the most hottest, let's say, contracts, or this is the hottest state of the world that is more, and these are the least. And you can scale them depending on the total gas that have been paid before, scaling them down by that, like the example that we saw. And you can execute them by dividing bids by local value. For example, if you don't want to do different prices, but just relative execution. So there are some examples. So there is the core blockchain that are working on applying some of these ideas. The application that they're thinking of is on native token transactions because you want that. Velocity of money is important if something is going to be a medium of exchange. So even if there are things that there can be an NFT drop, because even after L2s, if NFTs want one day to be used at the L1 level, they can still congest. But you want that even in the situation that your native token can be sent, so there can be ways to think of that. I'm open if you have any suggestions, questions, or discussion. Thank you.
Actually, this is more of an observation than a question. Do you think trying to optimize these goals of allocation of multiple resources, something like some local priority auctions with two-stage biddings probably would be like much more simplified option would be where a user is bidding for a global priority order and also to parallel service point, something like that.
Yeah, so a local price auction would be the more sophisticated way of doing this, okay? But here I just asked the very first question, like I think style of my paper I write in this is like, when would we even want to do it? And I think the example, the condition I didn't show is when you have high parallelization, which is that high parallelization, there is a notion of high parallelization and this depends, you want to do something like a local price auction. So you can interpret a lot of these fixed price things as local price auctions is the way you would do it to be incentive compatible broadly. But to analyze the market as a whole, you can look at it just from a fixed posted price.
Thank you.
Thank you. Theo. Okay.
So I may have missed this when you're describing the setting, but I'm curious, like you say, there's a local value for each piece of like state or contract or object. I'm curious what like your model of state here is, because if you're thinking about something like ETH with smart contracts, like you can't kind of a priori decide like these two contracts are separate because you could like call anything. So kind of like once you like that feels very hard to decide kind of in a dynamic sense or something of like, or you know what I mean?
Yeah. So let me give an example. Of course, I'm not a computer scientist, I'm an economist, so I will get it wrong, but I can try. So a transaction will touch different contracts, okay? And you can see, imagine you have the Uniswap pool that was, a bunch of people were trying to do an arbitrage on it. So you look at a transaction, all the contracts it was referring to, accessing, there will be one that will have a hottest measure because the total amount of gas paid on it before was the largest. So you can define that hotness there. So every transaction, you will assign it to that hotness. Now, you don't need to do this to have a queue for each of these. That's what I'm saying. You can have 4 buckets, okay? The very hot ones, the middle ones, and the less ones, okay? So, but there are architectures where it's simpler as an application, right? So there can be architectures like I gave an example of DAG-based structures. There are architectures now where they are already sending to different threads. The point I'm making also is when you're sending to different threads, if you don't have a global ordering and you can have this local ordering, you can choose where to send it, right? Right now, there is it's just a really kind of first come, first serve. You can choose where to send it by considering like this by hotness and define different relative prices. And I think also, in general, I think also there are some issues we discuss often, even if those are more micro. For example, we talk about MEV and how to deal with it. MEV is something that has to do with the fact that people are trying to exploit something that is about the value, the message that the transactions have. A transaction fee mechanism that only prices inclusion, right, doesn't refer to the value. And that's the point where you get here, that when it gets very congested, it becomes inefficient in that sense, if you can do the parallel pricing. Thank you.
So I was reading the SIMD 110, which was the Solana proposal for local fee markets. I was reading the GitHub comments for it, and one thing that I think Eugene brought up that was very interesting is people might try to rotate their contract and cool down the fee. Do you think that this is like something that just kills local fee markets with a 1559 style mechanism? Or do you think that there's a way to prevent people from rotating the contract to a new contract and then cooling down the fee that way?
Oh, so you're saying rotating it like within 10 minutes or something like that?
Yeah, like every 10 minutes, I just like copy all of the state into a new contract, and then that new contract.
But for the user to use that, how do you, or are you saying the user doesn't see the contract it's facing?
Well, I think you would abstract that away for the user, but the idea is the app would try to avoid these escalating fees by rotating to try and avoid getting super hot.
Yeah, I mean, so there can be many ways you think of how to game it. I think the optimal way you want to define hotness is you cannot do things within the same block. That's the problem because it's very gameable. But I think something at a high frequency like in EIP 1559, I would be hard pressed to imagine someone changing at every block. Now, if you wanted to, like I say, an example of thinking of this is not to say, okay, you can even say, okay, look, I care about velocity, like the example I mentioned. Like I think every blockchain you should be able to send the native token that it has. It's like if you want to use it as money. So that could be a simple thing, and that's something that is in control. It's one contract only, and you can have that have a different relative price. But there are certainly a lot of like implementation challenges that need to be thought through. Absolutely. Thank you.
All right, and standing between you and lunch is Theo Diamandis.
And for that, I apologize, so I'll try to be quick. Hi, everyone. My name's Theo. I'm a research partner at Bain Capital Crypto. Recently finished my PhD in optimization at MIT. This talk, as my talks normally are very much from the mathematical optimization perspective, and really looking at 1559, 4844, and associated transaction fee mechanisms from that perspective. So if you've seen my talk last year, which was kind of when we were still figuring out the online version of this problem, we looked at how to design multidimensional fee markets. This talk is taking the other perspective, is it's taking something that currently exists and saying, okay, in that framework that I presented last year, how does this fit in? What are the design choices that were made? And then as an open question, were these the best design choices? Could we do better? And so on. All right, so just to kind of get to the punchline, 1559 is a way to solve a specific online optimization problem with a particular algorithm that is low regret. And this talk is going to be going through each of these one by one. If you've seen my talk before, the online optimization problem is what I've introduced previously. Hopefully there's going to be some new stuff for everybody towards the end of this talk. So let's jump into that online optimization problem, and that's something I'm going to call the resource allocation problem. So all these pricing algorithms are ways to solve the dual of a particular resource allocation problem. The resource allocation problem is what you can think of how to price, how to pack an optimal block. And so pricing algorithms will say, okay, what prices do I set so that people pack optimal blocks for me? And let's first look at the single block model. This is going to kind of be a review from some of my previous work before we extend that into this multi-block online case. So just to formalize this very quickly, we'll look at a mempool where there's n possible transactions. Doesn't necessarily have to be a mempool, but imagine there are n possible transactions that can be packed in a block. Each of these transactions has some gas that it consumes, which I'm going to denote by the scalar AJ, and has some utility for the transaction submitter, which is going to be QJ. Then we have a binary vector x, which is just going to encode which transactions are included in the block and which are not. So xj is going to be 1 if transaction j is included and 0 otherwise. I'm also going to introduce the set S, which is just encompasses all of essentially the constraints that we have on these transactions. So this might include a gas limit, maybe it doesn't include a gas limit, it might include MEV constraints, anything where this transaction would be rejected or say some set of transactions would be rejected or considered invalid, is going to be in the set S. So there's a lot of complexity that's packed into the set S here. Then we can write the gas usage of the block as simply the sum of the transactions that are included, which I can conveniently write as the dot product between A and X. And the final ingredient is going to be the network's unhappiness with that particular gas usage. And that's going to be given by this loss function, which is a function of the amount of gas in that block. So as an example, and this is actually what 1559 uses, is the loss function is 0 if y is exactly equal to the target, or infinity otherwise. So this is just an indicator loss. This brings us to what this resource allocation problem actually is. And all it is saying is we want to maximize the utility of included transactions minus the loss incurred by the network, subject to the constraint that, that loss is a function of y, which is the resource usage of the included transactions. I use resource more generally. In this case, we're just talking about gas. And x is in the set of allowable transactions. Of course, I put this on here, and there's no way to actually solve this because the network designer can't choose what transactions are included. Block builders are the ones doing this, and doesn't know, or block builders or validators, and doesn't actually know the utilities queue. We'll see that we actually don't need to be able to solve this problem as it's stated here, because we can instead set prices so this problem is solved optimally on average. And this brings us to, instead of solving this problem, which I'll call the primal problem, we're going to be instead solving the dual problem. Duality theory and optimization says that we can take constraints, relax them to penalties. If we set those penalties correctly, then we solve the original problem. One key observation here is the network designer cares about the gas in the block, but doesn't really care about the transactions in the way that I've stated this problem, only cares about the transactions insofar as they imply a gas usage. Block builders, on the other hand, or users, care about what transactions are included. They don't really care about the load that's placed on the validators for resource usage. So naturally, this leads us to want to decouple the utilization of the network, which is y, and that of the transaction producers, which is kind of encompassed in x. And if we correctly set the penalty for essentially violating this constraint, then the dual problem will be equal to solving the original problem, and these utilizations will be equal. So to dive into what this dual problem exactly is, it's going to be find the gas price P. So this is like the price set by a fee mechanism that minimizes a dual function, which I'll call f. And from before, those P is exactly the price for violating that constraint, y is equal to A transpose x. This is the dual problem here. The particular form of it is somewhat important in that it decouples into two terms, one that's essentially a network term, which is this conjugate function. Looks like I have an extra parentheses there. And so you can think of this conjugate function as something that's pretty easily closed, like easy to compute, and usually has a closed form solution. So you think of this part as like easy. The second term is a little bit more complicated, so let's look at that in a bit more detail. What that second term says is maximize the net utility, so the utility minus the cost for the transaction, the cost being how much gas we have to pay, subject to those transactions being allowable. And of course, this is the exact problem solved by block producers, which means that the network can observe the optimal block for a given price, which I'll call x star. Putting these together, we can compute the gradient of the dual function f. And so that gradient is going to be first this y star, which is a function of p and falls directly out of the conjugate function. So think of this as something easy to compute, plus essentially just what the resource usage is of the previous block. One way to kind of interpret this gradient is y star is how much the network would be willing to supply, like essentially what the supply of a particular resource is given a price p. And this A transpose x star is going to be the demand. So how much of that resource our transaction producer is going to consume given that price. So the gradient then says essentially what is the mismatch between the supply, which is y star, and the demand, which is A transpose x star. That was the single block problem. Of course, this problem is not static, so we want to extend this to, to the multi-block setting. At each block, what ends up happening? Well, first, the network is going to choose prices, which are then published and known by everybody interacting with the network. Then the users are going to submit transactions, and so now I'm indexing everything by the time step t that we're at. Those transactions have some utility and some gas usage. I'm not going to make any assumption on the distribution of these transactions. They might be adversarial. I don't actually, there's no constraints on what the users can submit. After this, the network receives the payoff, which is that dual function. So now this payoff is also indexed by t, and it's just going to be that dual function of the resource allocation problem that I introduced earlier. So our new goal is, instead of just minimizing f at a particular price, we want to, for some time period, capital T, choose prices iteratively such that we minimize the average loss that we have. So essentially the average loss that we get from that dual function. And this is the online problem. All right, so now I'm going to actually talk about how do we solve this problem in practice, or how do you say base fee mechanisms that are implemented today, like 1559, solve this. One natural idea is you could apply an online mirror descent type algorithm to this. So mirror descent says to choose the next price, pt plus 1, such that it minimizes a linear approximation of the function, the dual function f, centered at the current price, plus a regularizer d, which is going to say I don't want the new prices to be too far from the current prices. So here, this linear approximation is just a first-order Taylor expansion centered at the current prices. And we also require that this distance function d is a strongly convex function that's going to keep, like I said, those next prices close to the current prices. So we don't want to go too far. As one example, you can recover vanilla gradient descent by using essentially a squared 2 norm to penalize the deviation from these prices. So that, if you plug this in, you'll end up getting gradient descent out of it. And there's a question of like, okay, well, what other regularizers d, or these distance functions, can we use, and what other types of properties do they have? EIP 1559 actually makes very specific choices here. First, as I said earlier, it chooses this loss function, that's this indicator loss, that says there's no loss if my resource usage is exactly equal to my target, which is 15 million, and it's infinity otherwise. This indicator might look very, very weird, but it actually turns out that even if you use a squared loss, once you kind of pass to the dual, it doesn't make that much of a difference, which is a bit counterintuitive, but you'll have to trust me on that one. More interesting, I think, is what this regularizer is. And so it uses essentially this regularizer that looks something like an entropy. So this p log p over pt minus p. If we plug this in, we recover the 1559 or 4844 update rule. Of course, 1559 is an approximation to the 4844 update rule, but I'm going to group these together for the sake of this talk. And that's just going to be that the next price is going to be the current price times an exponential of the usage minus the target. So this says how much we're deviating times some coefficient. I put up a loss function, I put up a regularizer, I tell you get 1559 or 4844. There's a lot of questions that we want to ask here, some of which I have answers to. First, what is this regularizer actually doing? Well, if we go ahead and plot it, we can see that this, from the form of it, is the Bregman divergence associated with the negative entropy function. It's not exactly the Bregman divergence. There's a constant offset here, but it's essentially that. So one immediate thing that we notice is this is asymmetric, and it penalizes decreases more than it penalizes increases. This might explain some previous results, like the Leonardo et al. Paper from, I think, FC in 23, that noticed the positive overshoot with 1559. So if we think about this positive overshoot, and we think about this regularizer, it's somewhat obvious that this regularizer would potentially lead to positive overshoot if we kind of have the price going negative and positive in equal proportions, given that it penalizes the positive overshoot less. Of course, stepping back a little bit further, we might want to ask, is this the right regularizer? Does this actually cause the behavior that we want or the dynamics we want out of this algorithm? Also, is this loss function a good one? Does it really make a difference what type of loss we have? As I said, if we use, say, a squared loss and this indicator loss with this regularizer, so you choose the loss function plus the regularizer, it doesn't make that much of a difference. So that might say that the loss function actually doesn't matter in this one-dimensional case. Furthermore, is mirror descent a good update rule? I think it's pretty general, so probably yes to this one. And though we have to say with what benchmark we measure good. And here I actually do have an answer for, but it's still, is that the right benchmark? Finally, a question that a few people in this room have spent some time on, what should that coefficient in the update rule actually be? And so I'll try to give at least some steps towards an answer to the last 3 questions in the rest of this talk. And we'll look at essentially this metric called regret. So why the algorithm works well with respect to a particular benchmark. This regret of the network comes from online learning, and we can think of it essentially comparing 2 scenarios. In the first scenario, we're doing this dynamic updating. So essentially, we're choosing a price, we're having some loss, we're using that to update the next price, and so on and so forth. In the second scenario, which is our benchmark, we actually see all the transactions that are submitted for whatever time period t we we care about. Once we see all these transactions, we choose one fixed gas price. And then we take the loss across all of these. Of course, to compute this P star, we need this crystal ball that says what are all the transactions that are going to be submitted for the entire rest of this time period. So it does require omniscience, but it also, our hands are tied in that we have to have that fixed price. One way to think about this in the machine learning context is the first scenario says I get my data point streaming. I have some initial, say, weight vector for my model or some initial parameters for my model. I get a data point, I make some prediction, I incur some loss, I use that to update my model. The second scenario says I get all the data in one batch. I train one model with a fixed set of parameters, and then I evaluate the loss on all of the data points. So this is why this online optimization metric is kind of intimately tied to the online learning setting as well, just for some intuition. So if we do choose the right step size, and a step size that, at least in this case, would look something like 1 over the target gas, which comes from that loss function, times 1 over 2 times, or the square root of 2t, times the log of whatever our maximum allowable price is. Since this is the square root of the log, this is going to be quite small. Then we get something, or that the regret is bounded by some constant divided by the square root of the time period we choose, capital T. So if you take t large enough, so if the time period is large enough, this regret goes to 0. Not at a super fast rate because of the square root, but it still goes to 0 as t gets large. And because of this, we can say that this algorithm is low regret. So mirror descent on this particular online problem with an appropriately chosen step size is a low regret algorithm. Okay, so this begs the question, well, does 1559 have the right step size? And recall that the more specific version of this is that it's approximately, and again, 1559 is a first order approximation to this, so this isn't quite right, but this is close enough. 1/8 times 1 over the target times the usage minus the target. So if we plug into that algorithm, we see that eta is 1 over 8 times 15 million gas. And we get 1 over root t regret with choosing eta is equal to 1 over the target times 1 over the square root of 2t. So if we compare these two things, this implies that 1559's choice of t, of the time window it considers, is only about 32 blocks, which is like 6.5 minutes or so. Because regret decays slowly with capital T, I would posit that this t is likely too small of a time window to consider, given if you want this to actually be low regret, because it decays as 1 over the square root, which would then imply that eta, so that coefficient, is going to be too large. And this has been observed by some others, including recent work from Malesh and Max that show kind of the oscillatory behavior of 1559. So just to kind of wrap up, what we saw is that 1559 is essentially solving a 1D resource allocation problem with mirror descent, or with online mirror descent, using a regularizer that's generated by the negative entropy function in a way that's low regret for an appropriately chosen step size. But there's a lot of questions that this kind of begs around what 1559 is actually doing. First, that I've covered in previous talks is, are we solving the right problem? Should this be a multidimensional problem? In that case, what are the resources that we want to actually consider? Should we use another loss function? More pertinent to this talk is the step size well calibrated? As I said, the theory that I presented here and empirical results suggest that it probably is not. We probably actually want a step size that's smaller, which would be essentially equivalent to considering a larger time window. And finally, should we choose another regularizer? This one I haven't thought that much about, so if anybody has perspectives on this, would be really open to those. And so for more info, please check out the paper. The paper looks at more of the designing part, but some of this stuff is in Appendix C. And please reach out with any questions. Also, these slides are on my website, which is just my firstname.lastname.com. Thank you.
Fascinating talk that come to the similar results, different approaches. So I wanted to just understand the role of the T, because you had it in your previous paper as well. Like, how can we discipline it further? Because if the the step size depends on T, I'm just curious if you have any thoughts of, is there anything that can discipline the choice of this T? Or it's just, yeah.
I mean, there's a trade-off here with kind of this, let's say, regret might not be, you have to choose a metric to say whether something is good. And I'm saying this is low regret. That doesn't necessarily translate to it being good. It's good with respect to this benchmark. And you can have very adversarial scenarios that are low regret, but where both of these terms will be quite large. So both essentially your online version and your offline version will incur high losses. And that's the trade-off you get with essentially smaller step size. This regret bound is going to be a lot looser, and so you might get more of that oscillatory behavior. A larger time window, so I reversed that. But larger step size, you get more of the oscillations. Smaller step size, larger time window, you're much closer to this fixed benchmark. But then there's a question of, well, what's the stationarity of essentially the price, like what prices should be? Because if you're looking at this fixed benchmark and you're in like a super non-stationary environment, then this fixed price benchmark is not necessarily a good benchmark. Fortunately, all these things can be really empirically tested with historic data, and we can see essentially what, kind of what time periods in the network would it be okay to have a fixed price, and use like those types of historical analyses to figure out what kind of this time window T should be. Of course, a few things is this T is rolling, so it's not like I'm considering one time window and then I'm starting from nothing and considering another time window. But it does, like I would say it kind of, the way I would set it is looking at like the stationarity of the historic transaction distribution. Of course, to here is this, all this applies for the multidimensional case as well. But with the multidimensional case, if you allow like essentially fixed price, say for different types of contracts, that actually might be like look quite different and might be quite a bit more stationary. or like over longer time periods than when you have one global price. I'm a big proponent of multidimensional fees. I feel like I've been talking about that for a few years now. So this talk wasn't about that, but this metric and all these results still apply. Yeah, hopefully not an answer, but a recipe to get an answer.
Also like multi-dimensional fees. So you had a slide with derivation of pt plus 1.
Yes.
Not this one. They're basically like constants. I was wondering about, there's some constants like 8 and...
Oh, for 1559 in particular,
Yeah,
I think.
Yeah, I was wondering, like, what would it take to make it a bit more continuous? And like, how, strict are those requirements?
Sorry, what do you mean continuous?
Like for, for the 8, 15 constants?
Oh, I see. So this is what's being used. So this is like with that particular loss function and the particular regularizer, this is the update rule that you get. And so this is, the way 1559 is implemented right now is you take the first order Taylor expansion of that exponential term, and so it ends up being 1 plus 1/8 times usage minus target over target. But what I'm saying is like essentially if you take this eta and compare like what I get to what 1559 gets, and this is kind of what you come up with. Maybe you can dynamically choose this coefficient eta as well, so that's another thing that you could do. You actually get lower regret. It's just those are much harder to implement and usually require some notion of like a start time. Because typically if you dynamically choose that, you have something that corresponds to the current iteration that you're on. So I'm not sure if that answered your
Yeah, I was basically wondering exactly about that. Okay, thank you.
Yeah, it's something that you can do. It just, let's say if you don't know what the T that you're at actually is, or if you're trying to kind of roll these windows, then unfortunately there's like not a really, or maybe, I'm not sure if there's not, but I haven't come up with an easy way to do a dynamic eta in a way that makes sense. Because in some sense, you also want this to be like almost memoryless, where you start it at some point, but it doesn't really matter what the initial parameter is that you started it, because we expect these things to run continuously in production for a very long period of time, versus there being like some like kind of learning phase where we learn the optimal prices, and then we don't want to change that much after that. But if you have any ideas to that extent, like I would love to. It's something where if you can do that, you can go from like 1 over root T regret to 1 over T regret, which decreases quite a bit faster compared to this fixed baseline.
Yeah, so thank you.
Hey, quick question. So in your definition of regret, you force the omniscient, ex post decision to only fix one P star. Is there a world where it would make sense to compare it to choosing the min over the P at each time step versus just fixing one P star?
You just get like 0 then.
Why is that?
Essentially, so think of like the online learning case for a loss function. If you could choose the exact like minimum weights for a particular data point, you could essentially get loss 0. So it's kind of, yes, you can do that, but in that case, the benchmark is a little bit too strong almost.
I see, yeah. So I guess given the stationarity thing you were describing before, could it make sense to try and like have a few prices that you're targeting? Like, given there's like big regime shifts in the base fee, like maybe there's like a low base fee and a high base fee.
Yes, in that case though, there's a question of, so there's like the multidimensional route, which is kind of one hand. So you try to decouple things that should be priced differently, and then that is captured in this baseline. And then there's the route of you have some classifier for things that come in, I guess, that says, oh, you can delay it or not. That changes the mechanism part, so I'm not sure how to, I think it would just require like analysis of a new mechanism, which you could probably do with similar tools. This is just kind of the V1, I suppose, online learning analysis of these things.
Cool, thanks.
All right, so that wraps up the session. We have exactly 1 hour for lunch, which will be downstairs where you walked in, and we will resume at 1:20.